So in this video, we're going to graph some sine functions. We're going to start off with just sine for now. We talked about this earlier in class, kind of how a sine graph looks. Remember that it looks like a wave. It's a wave that repeats with, crests and valleys and crests and valleys. So I'm going to start with my axes, f of x and x. On the x-axis, I'm going to go from negative pi, or negative 2 pi, to positive 2 pi. So on the right side there, I did 0 to 2 pi first. On the left side, I'm going to go all the way to negative 2 pi. And for my y-axis, my f of x axis, we're going to go from negative 1 to 1. Because if you recall, the regular sine function goes from negative 1 to 1. Alright, so let's plot some points. So again, you really have to know some trig values off the top of your head. Sine of 0 is 0. Sine of pi is 0. Sine of 2 pi is 0. So all those values result in f of x being 0. Other critical points, sine of pi over 2 is 1. Sine of 3 pi over 2 is negative 1. Sine of negative pi over 2 is negative 1. And sine of negative 3 pi over 2 is positive 1. So really have to know those critical points. So when you put in these last coordinates, you do see this wave-like graph that will repeat infinitely in the negative x and positive x directions. So while we talked about what the graph looks like earlier, we never really talked about critical information from the equation. So every sine function, when you're graphing, is written in this general form. A sine k parentheses x minus b. And each of those things, a, k, and b, tell us really important things. The absolute value of a is the amplitude of the curve. And I'll talk about what that is in a sec. K is important because 2 pi over k is the period of the curve. And I'll talk about what that is in a sec. And then finally B is important because it tells us how we shift the graph. It's the phase shift of the graph. So back to what A is. A is the amplitude. And what the amplitude is it's half the total height of the curve. So if you think about kind of the center to the top, that distance is the amplitude. The period is how long it takes to make one full wave of the curve. So how long does it take to make one full wave? That is the period. And B is the phase shift, which is basically how far left or right from center that we're going to shift the graph. It's a left-right horizontal movement. That's what the phase shift is. So let's look at the one we did. In the graph we did together, A is 1, right? A is 1. So that is half of the total height of the curve. So if you go from the center to the top, that distance is 1. So the center to the top, or the center to the bottom, that is 1. That distance is 1. the overall distance is 2. The period. In our problem that we did together, k is 1, right? The number in front of x is 1. So 2 pi over 1 is the period, how long it takes to make one full wave. And we see that in our graph, that it takes 2 pi, takes a distance of 2 pi to make one complete wave. And finally, the phase shift b, how far are we moving it left and right? Well, in our example, there was no b. B was 0. So we are not shifting it at all left or right from center. So let's do an example here together. In each problem, I want you to identify the amplitude, the period, and the phase shift. So for our example, let's do f of x equals 3/4 sine 2 parentheses x plus pi over 3. So let's see if we can identify each of these characteristics. The amplitude. Well, the number in the very front, a, is 3/4. The absolute value of 3/4 is 3/4. So that is our amplitude, which again kind of represents the height of the wave from center to top. That is the amplitude. So if you were thinking about the total height, this means that the total height is 3/2, because 3/4 times 2 is 3/2. So the total height from very bottom to very top is 3/2. Okay, next is the period. To fully understand the period, we look to the value of k. In our current example, k is 2. So to calculate period, we do 2 pi over k. So 2 pi over 2 reduces to pi. 2 pi over 2 is pi. So that is the value of my period. We're going to make one complete wave in a distance of just pi. So just writing it out for you here. This means that one complete wave is done in a distance of pi. Finally, the phase shift. We're going to want to look to our value of b. So the phase shift in our example, pi over 3. And we're going to kind of go against that sign. So since pi over 3 is positive in our equation, we're going to move to the left. We're going to move left pi over 3 units. This kind of movement resembles what we would have done when we were in vertex form of a parabola. Remember, we kind of went against the sign. So our phase shift is pi over 3 units to the left. So with all those things in mind, we can have a sense of what this graph looks like now. We are going to want to graph these. The whole point of identifying these characteristics is to be able to graph them. So let's see what it looks like when we graph. So here are my axes. And first I'm going to graph the original sine x. So in order to kind of see how each characteristic affects the graph, I'm first just going to graph plain old y equals sine x. And this is basically what we did in the beginning of this video. We graphed y equals sine x. So here's what that looks like, right? This has an amplitude of 1. It has a period of 2 pi. Nothing special about this. So what happens when we apply our amplitude of 3/4? Our amplitude is 3/4, which means middle of the curve to the very top is 3/4. Middle of the curve to the very bottom is also 3/4. So how's that going to look? Well, I pencil it in, and I'm also going to apply my period. My period is pi. So not only did I apply my amplitude of 3/4, but I applied my period of pi. So in a pi distance, one complete wave occurs. So that means in a 2 pi distance, 2 complete waves will occur. I'm going to do the same thing over here on the left side of my graph. Amplitude is 3/4. Period is pi. So one more complete wave, amplitude 3/4, and period of pi. So that's what it looks like when you apply the amplitude and when you apply the period. And I'll make it in dark red here so you can kind of see the difference between the original graph and the new one with amplitude and period applied. Alright, so after I finish this up, making it solid red, you'll see the total difference between the original graph and the new one. So this one hasn't applied our phase shift yet. So right now I'm just pointing out that the amplitude is 3/4. But we haven't applied our phase shift yet. So we're going to go pi over 3 units to the left. Again, we're going to kind of go against the sign. We're going to go against the plus sign in our equation. So we're going to go pi over 3 units to the left. So I just start from the very center. Very center, go pi over 3 units left. And then the rest of the curve is going to be parallel to that one in solid red. So once you've moved 1 unit pi over 3 left, just complete the graph by drawing it parallel. So first I did the right side, now I'm doing the left side. Again, making it parallel to the solid red line. So this black line represents my final graph. The black line has applied the amplitude, the period, and the phase shift. And that's what it looks like. So it can be kind of hard to see on paper. Let's try to see what it looks like on Desmos.com. So whenever you're graphing on paper, I highly suggest that you use Desmos as a tool. It's very powerful. It can make sure that you're doing it correctly. One thing you want to do though, let's change it to radians on our x-axis. So if you hit the wrench in the top left corner, you see a step option. Under step, hit pi, and that'll change the x-axis to measurements of pi. So now you see it as pi over 2 pi. So whenever you're doing trig graphs, let's have that for our x-axis. So far I've just graphed sine x. So naturally our period is 2 pi. Our amplitude is 1. So let's see what happens when I add a 3/4 in front of sine x. So in green here, I have y equals 3/4 sine x. And sure enough, there is my new amplitude. My new amplitude is 3/4. So it is a shorter graph than the original. But my period so far is still 2 pi. So both the red one and the green one both have a period of 2 pi. Okay, let's make a third graph. Let's keep the amplitude of 3/4, but let's change the period to pi. So in order to do that, I need sine parentheses, or 2 parentheses x. Let's keep that 2 outside of the parentheses. So doing that, we have a blue graph here, and the blue graph is definitely showing a period of pi. The blue graph has an amplitude of 3/4, but it now has a period of pi. So the last step is to phase shift that guy pi over 3 units to the left. So my final graph is y equals 3/4 sine 2 parentheses x plus pi over 3. And again, make sure that 2 is outside of the parentheses. Alright, so there you go. And like I was trying to explain, here the blue and the black graph are parallel. So that's what I was trying to kind of explain as I was doing it on paper. That as soon as you have a point that's phase shifted pi over 3 units to the left, let's complete the curve by drawing it parallel to the one before it. Alright, so when graphing on paper, that's kind of how I want you to do it. I want you to do it in steps. So first start with sine x, then apply the amplitude, then apply the period, then apply the phase shift. So kind of do it in steps till you get the last graph. Alright, let's do one more together. For this one, I want you to identify the amplitude, period, and phase shift. So the original graph is f of x equals 2 sine parentheses 2/3 x minus pi over 6. So I intentionally wrote it like this with everything in the parentheses for a reason. Sometimes it's going to be written a little different like this. In our very beginning, k was outside of the parentheses. So you may have to do that as a pre-step. So I need to factor something out to get just x in the parentheses. I need to factor out 2/3. So when I factor out 2/3, I'm left with parentheses x minus something. So what is that something? Well, on the side of my paper here, I'm going to do 1 over 6 divided by 2/3. Basically, I'm going to factor out 2/3 from 1/6. So 1/6 divided by 2/3 is 3 over 12, or 1/4. So when you factor out 2/3, you're left with pi over 4. And to confirm that, just do a quick check. If I were to distribute in 2/3, I'd get 2/3 x minus 2 pi over 12, which reduces to pi over 6. So I did do it correctly. So now that we're in this form in which k is outside of the parentheses, I can identify my amplitude. Amplitude is absolute value of 2, which is 2. My period is 2 pi all over 2/3. So that has to be reduced here. 2 pi over 1 divided by 2/3 is going to result with 3 pi. So my period is 3 pi. And then finally my phase shift My phase shift is pi over 4 units to the right. I'm going to go the opposite sign from minus, so I'm going to go pi over 4 units to the right. So these three characteristics should give you a sense of what this graph's going to look like. Because of the amplitude being 2, it's going to be a slightly taller graph than sine x. Because of the period of 3 pi, it's going to be a slightly wider graph than the original sine x. And because of the pi over 4, it's going to be shifted a little bit to the right. So try to have that picture in your head. And again, I use the term taller and wider a little bit loosely. It's kind of hard to have a taller sine graph or a wider sine graph. But I think you get the idea of what we're trying to explain there. Okay, another example here. What if my equation was negative 2 sine parentheses x minus pi over 3? Well, my amplitude would be the absolute value of negative 2, which is positive 2. The period, well, k is 1 here. The number in front of the parentheses is 1. So my period is 2 pi. And my phase shift is pi over 3 units to the right. So I'm going to move the original graph pi over 3 units to the right. All right. One quick note about all three of these. How is the graph going to look at the end? Well, because of the amplitude, it's going to be, again, slightly taller. Because of the period, it's going to be the same width as a normal sine x graph. So a normal width. And because of the phase shift, it's going to be shifted, again, a little bit to the right. So one thing to talk about with the amplitude. Because we're doing absolute value of A, the amplitude is always positive. So when describing amplitude, it's always a positive number. But even though the amplitude is always positive, that negative out front is doing something. So what is that negative doing? Well, let's think about it. If I were to draw a normal sine x graph, we've done a few of those already in this video. How does a normal sine x graph look? Well, it starts in the center. 0, 0 is a point on it. It moves up and down. It moves up and down. But what would happen if there was a negative out front? If there was a negative in front of the sine, all the y values would be turning positive to negative and negative to positive. So that is flipping the graph about the x-axis, right? If all the negative y values turn to positive and all the positive y values turn to negative, that is reflecting the graph across the y or x-axis. So even though our amplitude is positive 2, that negative still had a significant impact. So if you ever see a negative out in front of the graph for your A value, that's going to reflect it about the x-axis. So just be aware of that. Last problem we're going to do together. I'm going to give you a picture of a graph, and I want you to write the equation. So here is a problem from your book. They're giving you the graph, and they want you to write the equation. So basically, we need to identify the amplitude, we need to identify the period, and any possible phase shift. So we need to identify those three things. Well, based on the picture, it looks like my amplitude is 2. From the middle of the graph to the peak, or from the middle of the graph to the bottom, that amplitude is 2. What about the period? How much distance does it take to make one complete wave? Well, one complete wave is completed in a distance of pi. So my period is 1 pi. And then finally, my phase shift. Well, the phase shift might be kind of hard to identify. To properly do this, let's think about the sine graph. At the very center of the sine graph, we were at 0, 0, and as we moved right, we moved up. Right? So from the center, and as we moved right, we went up. So where is that point on this graph? Well, that point is right here. I'm pointing to it right now. It's at 3 pi over 4. So it looks like we went from the very center, 3 pi over 4 units to the right. That was our phase shift. So our phase shift is 3 pi over 4. So with these three characteristics, we should be able to write an equation of our sine graph. Basically, we just got to input our A, K, and B values. Well, A and K are pretty easy. A and K are pretty straightforward. So out front, I'm going to have sine, and in my parentheses, I'm going to have x minus 3 pi over 4. And for now, I'm going to leave K as K, because it's going to take a little bit of work on the side to get the correct K value. So how do we get period? Well, period is 2 pi over K. And based on the picture, we know the period is equal to 1 pi. So this little equation will enable us to solve for K. So solving this equation, we get 2 pi equals K times pi. So K equals 2. So that's how we can get our K value every time. Once you identify what the period is, set it equal to 2 pi over K and solve for K. So my final equation, 2 sine 2 parentheses x minus 3 pi over 4. That is the equation of the graph that we saw the picture of. And like I always say, let's use our trusted friend Desmos. So let's check our work. When I put into Desmos the equation that we wrote together, I just want to see if we get the same picture as the one that's in our book. So the one that Desmos shows us has an amplitude of 2. It has a period of pi. So it should resemble the picture from our textbook. So if I get out of Desmos here, and if I go to our pictures, it is the same picture. A amplitude of 2, a period of pi, and a phase shift of 3 pi over 4.